water, and some of this has to be removed by evaporation in order to reduce the wort to the necessary volume and gravity. A moment's consideration will show that in the brewing of say 100 barrels of beer, it is necessary to use much more than 100 barrels of water, quite apart from that required for washing purposes and for cooling. In the first place, the spent grains left in the mash tun retain a considerable quantity amounting to nearly 30 gallons for every quarter of malt mashed. Then there is the loss by evaporation in the copper, and subsequently during cooling, the quantity retained by the hops in the hop back, and finally there is a small loss due to the transference of the wort from one vessel to another. Speaking roughly, it may be said that in the actual brewing of 100 barrels of beer about 130 barrels of water would be required. Brewers' coppers vary a good deal in construction, the majority being open, whilst others are closed and so constructed that the wort can be boiled under slight pressure. The effect of the increased pressure is, of course, to raise the boiling point of the wort a few degrees and to bring about the extraction of rather more matter from the hops than would be the case with an open copper. It may be doubted whether this is ever desirable, and the general consensus of opinion is undoubtedly in favour of boiling under ordinary atmospheric pressure. Boiling by steam is largely replacing the older method of fire boiling, being cleaner and more convenient and more economical. When the wort has been boiled for the requisite time, usually about 2 hours, it is allowed to flow from the copper into a wooden or metal vessel known as the hop back. This may be of any convenient shape, usually round or rectangular, and is provided with a false bottom consisting of a series of perforated metal plates. The object of this vessel is to retain the spent hops, and to allow the wort to be drawn off in a fairly bright condition. Since the hops absorb a good deal of wort, it is usual either to wash this out by sparging with hot water, as after mashing, or to obtain it by means of a suitable press, to which the residual spent hops are transferred. The layer of hops which covers the false bottom acts as an excellent filtering medium, keeping back the coagulated proteins referred to above, and enabling the wort to pass to the next stage in a purer and brighter condition. From this point of view it is obviously desirable that the area of the hop back should not be too large in relation to the volume of the wort to be dealt with, so that a layer of hops sufficiently deep for good filtration may be obtained. It may perhaps be mentioned here that the quantity of hops used in the brewing of beer in this country varies from about 1 pound per barrel of beer in the case of mild ales, to 4 or 5 times that quantity in the case of fine pale ales, strong stouts, and certain export beers. When sugar materials, invert sugar, cane sugar, glucose, etc., are used, it is customary to dissolve them in a separate vessel and to run the solution into the copper, or they may be added directly to the wort in the copper itself. In Chapter 3 reference has been made to the fact that the various classes of beer require for their production water of different mineral character, if the best results are to be obtained. Taking on the one hand a soft alkaline water, such as is obtained from the deep wells in and around London, and on the other a hard gypseous water, such as that derived from the wells in Burton-on-Trent, it may be useful to refer here to certain differences which these waters exhibit and which are of importance from the brewing point of view. In the first place, the softer water will prove rather more extractive in the mash tun and also in the copper. From the hops it has a tendency to dissolve certain coarse and unpleasant bitter substances which are not dissolved to the same extent by the harder water, and it also produces wort and beer of a rather higher colour. Worts, moreover, which have been brewed with the hard gypseous water, break better on boiling than those brewed with the soft alkaline supply. That is to say, the coagulable proteins which are rendered insoluble during boiling form larger and more coherent masses, and so are removed more completely during the hop back filtration mentioned above. End of chapter 4. Of Brewing by A. Chaston Chapman. This LibriVox recording is in the public domain. Read by Marianne. Chapter 5. Cooling. The next stage in the conversion of malt into beer is the cooling of the wort to the temperature at which the yeast is added and fermentation commences. Simple as this statement may appear, the cooling of the wort is one of the most important and, in some respects, most troublesome of all the procedures which go to make up the brewing process. The mere lowering of temperature presents, of course, no difficulty, but it has to be remembered that wort, even when hopped, is not an unfavorable medium for the development of a variety of living organisms, which as the result of their life activities bring about chemical changes which may render the resulting beer unpleasant in flavor or even quite undrinkable. As will be seen later such organisms may be either bacteria or certain species of yeast, and the chief aim of the brewer at this stage is to cool his wort to the required temperature and at the same time to protect it from infection by such undesirable organisms which are always present in the air. As a general rule, the cooling process takes place in 3 stages. In the first place there is a small reduction of temperature during the short time the wort is in the hop back, then there is a further considerable lowering of temperature in the cooler, and finally the temperature is reduced to the required point by being passed over one or more refrigerators. The cooler is a shallow rectangular vessel made of iron, copper, or wood, and is usually situated near the top of the brewery and in such a position that air may have free and ready access to it. As this vessel is almost invariably at a much higher level than the hop back, the wort is pumped from the latter vessel on to it and allowed to remain as a rule until its temperature has been sufficiently reduced to permit of its being run over the refrigerator. Since on the cooler the wort is only a few inches deep and consequently presents a very large surface to the air, it is clear that under ordinary circumstances immense numbers of organisms of various kinds must fall into it. As a rule the room in which the cooler is situated has open louver boards on all 4 sides, so as to allow as much air as possible to pass over the cooling wort and to facilitate the escape of steam. As, moreover, breweries are usually built on or very near to main roads, it will easily be understood that the air which obtains access to the wort, particularly during dry, dusty weather, is very rich in all kinds of microorganisms. Prior to the introduction of refrigerators, the wort had to be cooled entirely on the cooler, which frequently necessitated a sojourn of 24 or 36 hours, particularly during the summer months. It will be readily understood that under such circumstances it was often impossible to brew beer possessed of reasonable soundness, and so notwithstanding their greater alcoholic strength as compared with the beers of today, and the larger proportions of hops used in their production, they were frequently sour and undrinkable, almost at racking. In fact it was found that beers which had to be stored for any time could only be brewed during the winter months, and even then their stability was often very problematical. The introduction of refrigerators marked an epoch in brewing practice, since it enabled the brewer to cool the wort to the required temperature in a very short time and with a minimum exposure to the air. Refrigerators are ordinarily of 2 forms, the vertical and the horizontal. In both, however, the principle is the same, the wort running over metal tubes through which cold water is made to flow. The cold water in the vertical form, Fig. 3, is admitted to the lowest tube at A and thence passes successively to the others and finally flows away at the top, B. The wort passes from the trough, C, through a series of small holes in a thin film over the outer surface, and when it reaches the pan, D, has been reduced to the temperature necessary for the addition of the yeast. In the majority of breweries at the present day, both a cooler and a refrigerator are employed, but sometimes the cooler is done away with entirely or is replaced by a deep receiving vessel, a system which has much to recommend it, as I shall show later. It should be said, however, that the cooling of the wort is not quite the only function of the cooler. Certain of the constituents of the wort have the property of absorbing oxygen from the air at tolerably high temperatures, and this hot aeration, as it is called, to distinguish it from the cold aeration or absorption of oxygen by the cold wort while passing over the refrigerator, is very generally regarded as beneficial. It is true that some authorities have questioned its importance, but I think there is a general consensus of opinion that these more or less obscure oxidation changes are desirable and that they do exert an appreciable effect on the brightening capacity of the finished beer. It is fortunate, however, that these changes occur most actively at elevated temperatures, about 180° Fahrenheit, and it is very doubtful whether much if any advantage in this direction is gained by allowing the temperature of the wort on the cooler to fall below, say, 160° Fahrenheit. A further function of the cooler is to permit of the deposition of the coagulated protein matters from the cooling wort and to leave the bulk of these behind when the wort is run down over the refrigerator. This insoluble deposit is technically known as the cooler sludge. There can be no doubt that if the wort on the cooler could be reduced to a comparatively low temperature under conditions rendering bacterial infection impossible, the shallow vessel of large area has much in its favor. In practice, however, it is very difficult, and many brewers have found that they can secure the main benefits of a cooler without its serious drawbacks by substituting for it a deeper vessel of much smaller area. By spraying the wort pumped from the hop back into such a vessel, sufficient hot aeration is secured, and if it is not possible to keep the protein sludge back as completely as with a cooler, the advantages on the score of diminished infection are so great as to render this consideration of little importance. Above 150 degrees, the wort is practically sterile, and the brewer should endeavor by every means in his power to ensure that the temperature of the wort when it reaches the refrigerator shall not be appreciably lower. Assuming the wort to be for all practical purposes sterile when it reaches the refrigerator, the next consideration is how to avoid serious infection while the wort is passing over that piece of plant. It has been pointed out that the wort runs over the refrigerator tubes in a thin film. This is clearly necessary in order to secure rapid cooling, and it will be obvious that the surface exposed to the air by a brewing of say 100 barrels must be enormous. The adequate protection of the wort at this stage does not, however, present any very serious difficulty, since it is not a difficult matter to enclose the refrigerator, or refrigerators, in a tightly constructed room capable of being supplied with filtered air, and this is the procedure adopted in most modern breweries. The purification of the air from microorganisms is effected in many ways, such as by passing it over numerous trays containing jelly, or by causing it to traverse cotton wool or other filters, the filtering material being usually kept moist in order to increase its efficiency. The air so filtered is then injected by means of a fan into the refrigerator room, and in this way the steam is removed and the surface of the cooling wort is brought into contact with a constant supply of pure air. Whilst it is necessary to protect the cooling wort from airborne infection, it is also of the highest importance that the refrigerator itself should be in a scrupulously clean condition. And the efforts of brewers' engineers have during recent years been directed to so improving the design and construction of this important appliance as to render cleaning a simple operation and the lodgment of dirt practically impossible. Unless the greatest care is taken, dirt is very liable to accumulate in the corners where the tubes enter the upright supports, and as this will always contain innumerable living organisms, it is quite easy for a whole brewing to be infected and spoiled by being passed over a refrigerator which is not properly clean. It will be seen then that infection of the wort may occur either on the cooler, whenever the temperature falls appreciably below 140 degrees Fahrenheit, or on the refrigerator, and may be caused either by airborne organisms or by those derived from contact with dirty surfaces. As showing the amount of infection which may be caused by a refrigerator which has not been thoroughly cleaned, I may say that I have on many occasions found the wort at the top of the refrigerator practically sterile, whilst samples taken from the same time from the pan have contained as many as 3,000,000 organisms of various descriptions per litre. Fortunately, numbers such as these are not as terrible as they may at first sight appear to be, since hopped wort and beer are not very favourable media for the growth of bacteria in general. Thus, Zeix has shown that of 107 varieties of bacteria experimented with, including bacilli, micrococci, sarcinae, and spore-forming bacteria of various kinds, only 15% could develop in hopped wort, provided that the wort was simultaneously seeded with yeast, and that only 2% were capable of growing in beer at 10 degrees Celsius and 3.7% in beer at 25 degrees Celsius. On the other hand, it must not be forgotten that bacteria reproduce with enormous rapidity under favorable conditions, and that the organisms which are capable of bringing about disease changes in beer are of very widespread occurrence. Zeix's experiments, which dealt more particularly with water bacteria, are in accord with some of my own observations in connection with airborne bacteria, for I have observed that in many cases the proportion of bacteria capable of developing in hopped wort does not exceed 5% of the total number falling in. This fact points to an important difference between infection due to chance air-carried organisms and that caused by dirty surfaces, such as I have referred to above. In the latter case, the organisms which have survived as the result of a kind of natural selection are all capable of growing in hopped wort, and many of them in beer. They are in fact all effective, and a given number thus introduced is almost certain to have a much greater effect on the wort and beer than a similar number falling in from the air. It must be remembered, moreover, that bacteria are not the only organisms which the brewer has to fear, since some species of yeast are pathogenetic to beer, and these flourish without exception in both wort and beer. These so-called wild yeasts, to distinguish them from the industrially useful, or culture yeasts, are usually present in considerable numbers in the air from June to September, after which date they rapidly diminish. Growing as they do on the surface of ripe fruits, such as cherries, plums, strawberries, etc., it will be obvious that wort infection by these yeasts is more likely to be serious in the case of breweries situated in the country and in the neighbourhood of orchards and fruit gardens, than in those in towns, although this is not by any means always the case. Since the thermal death point of these yeasts is usually about 140° Fahrenheit, it follows that no infection is to be feared on the cooler if the worts are run down at or above that temperature. It is while the wort is running over the refrigerator that such infection is most likely to occur, and as has been indicated above, this can be almost entirely prevented by taking care that the refrigeration is carried out in an atmosphere of purified air. From the above it will be gathered that the operations of the brewer are greatly complicated and rendered much more difficult by the necessity of working under what may, for want of a better term, be called aseptic conditions. Mere cleanliness is not sufficient, and the modern brewer has to be almost as constantly on his guard against the introduction of pathogenic organisms as has the modern surgeon. In 1875 Pasteur, as the result of his epoch-making labours, wrote the two following sentences: "Every unhealthy change in the quality of beer coincides with the development of microorganisms foreign to brewer's yeast, properly so called. The absence of change in wort and beer coincides with the absence of foreign microorganisms." These two short statements embodied a great truth, and virtually marked the transition from darkness to light and from chaos to order. Somewhat extended and modified as the result of more recent research, they are recognized as the foundation stone on which so much of modern brewery practice is built, and without which real success, if attained at all, would be largely a matter of chance. It has already been stated that in some breweries, where the cooler has been abolished, there is not even a collecting vessel, and the wort is pumped from the hop back directly over the refrigerator. I do not think this is altogether the best system, but it cannot be denied that in many cases it yields perfectly satisfactory results. A greater strain is, of course, thrown on the refrigerators, which must have a larger cooling capacity than would otherwise have been necessary, that is to say, if the wort is to be cooled down in reasonable time. It is customary in some breweries to pass artificially cooled water through the lower tubes of the refrigerators, and thus to increase their cooling power. When there is refrigerating machinery, the plan is a good one. While the wort is passing over the refrigerator in a thin layer, it absorbs oxygen from the air, that is, of course, as soon as the temperature has fallen sufficiently low. This dissolved oxygen is of importance during the next stage of the process, since it is necessary for the proper activity of the yeast. End of chapter 5. Part 1 of Brewing by A. Chaston Chapman. This LibriVox recording is in the public domain. Read by Marianne. Chapter 6 Fermentation Part 1. The wort having been cooled to about 60° Fahrenheit passes from the refrigerator to the vessel in which the process of fermentation is to be carried out. Here the requisite amount of yeast is added, and the contents of the vessel are thoroughly mixed. Before proceeding farther, it will be necessary to devote some little space to the consideration of yeast as a living organism, and then to discuss at somewhat greater length the nature of the process of fermentation so far as it is at present known. If a little ordinary brewer's yeast be mixed with water and examined by means of the microscope, it will be found to consist of a number of bodies, some approaching the spherical in their contour, others being more or less ovid. Fig. 4. Each of these is a self-contained organism, consisting of a single cell. On examining these cells more closely, it will be seen that each is bounded by a cell wall, which encloses the protoplasm and other cell contents. In the younger cells, the protoplasmic contents are clear and transparent, but as the cell grows older, the protoplasm becomes more granular in character, and one or more cavities known as vacuoles may be observed. These vacuoles consist of the cell juice, which at certain stages of development is disseminated throughout the protoplasm, but later tends to collect in one or more parts of the cell. These cells are very minute, having an average diameter of only 1/120th millimeter (1/3000th of an inch) and an estimated volume of .0000004 cubic millimeter. It has been calculated that an ounce of pressed yeast would contain no fewer than 50,000 million cells. Minute as they are, however, each of these cells is the seat of vital processes of the greatest complexity, and may, without exaggeration, be said to constitute a laboratory in which are carried out chemical changes which the most highly trained modern chemist is powerless to imitate. If a little young yeast is examined microscopically, it will be seen that many of the cells are not single, but have smaller cells attached to them, whilst in some cases chains of 3, 4, or even more may be observed (Fig. 5). This is the chief mode of reproduction, namely by budding. The bud occurs first as a small protuberance on the surface of the cell. This quickly increases in size until it has attained roughly the dimensions of the parent cell, after which it becomes detached, leading a separate existence, and in turn reproducing by the same process. It often happens that before the offspring cell has separated from the parent cell, it has itself commenced to bud, and so chains or clusters of connected cells may often be seen. Yeast is capable of reproducing itself in another manner than by budding, namely by the formation of internal spores or ascospores. The conditions which favor this mode of reproduction are the employment of young and vigorous cells, a moist surface, plenty of air, and a suitable temperature, usually about 25°C. Under these circumstances, and at the end of about 24 hours, certain changes will be seen to be taken place in the protoplasmic contents of many of the cells. The protoplasm becomes at first more granular, and then signs of segregation become visible, the contents of the cell separating into several ill-defined portions, usually from 2 to 4, but in some species as many as 8. A little later these segregated portions of highly granular protoplasm become invested with a membrane, and it can then be seen that the original cell contains sometimes one, but usually 2 or more well-defined spores (Fig. 6). During the formation and development of the spores, the parent cell swells considerably, and in the end bursts, liberating the spores, each of which constitutes an individual yeast cell and is capable of reproducing in the ordinary way by budding. During recent years much study has been devoted to the precise mechanism of reproduction in the case of yeast. For long it has been known that every yeast cell contains a nucleus, but the true nature and function of this has only comparatively recently been made clear through the work of Janssen and Leblanc, and especially of Wager and Peniston. The last mentioned authors have shown that every cell possesses a nucleus and a nucleosis, and they have adduced a good deal of evidence to prove that the former is identical with the main vacuole of the cell, and that the latter is a homogeneous body which is always found to be in close contact with the nuclear vacuole (Fig. 7). During budding, division of the nucleus takes place, accompanied by constriction into 2 approximately equal parts, one of which passes into the bud, whilst the other remains in the parent cell. During ascospore formation, the vacuole disappears and only the nucleosis remains. This, however, divides into 2 by a process of constriction, and each of these 2 parts again divides into 2, so that 4 nuclei are formed, each of which becomes the nucleus of a spore, and consequently of a new cell. Barker has called attention to a process of true conjugation in the case of certain species, in which he gave the name zygosaccharomyces. Under certain conditions, cells of this yeast formed buds which gradually developed into long beak-like processes. When the beaks of 2 adjacent cells touched one another, union took place, the tips of the beaks disappeared, and a tubular connection was so established between the 2 cells, each of which then produced 1 or more spores. Interesting as these phenomena are to the biologist, they do not closely concern the practical brewer, since under the ordinary conditions of the brewery yeast always reproduces by the process of budding. Unlike certain other unicellular organisms and the higher plants, the yeast cell contains no chlorophyll, and is not therefore able to obtain its carbon by the decomposition of carbon dioxide. In this respect it resembles the fungi, in which great natural family it is included. Owing to its ordinary mode of reproduction, it is classed among the budding fungi, and lastly its ability to form ascospores completes its claim to belong to the genus Saccharomyces, a group which comprises all the important organisms which produce alcoholic fermentation. Like all fungi, the yeast organism uses up oxygen and gives off carbon dioxide, and it is for this reason that a supply of oxygen is necessary if the vigor of the yeast is to be maintained during fermentation. This point will be referred to again when dealing with the theories which have been put forward to explain the process of fermentation. A close investigation of the Saccharomycetes has revealed the fact that the genus includes a considerable number of species, many of these differing widely in their fermentive and other properties, and that certain of these species can be again subdivided into races or varieties. Even at a comparatively early period, certain well-marked morphological differences were noticed as the result of microscopical examination. Thus some yeasts formed spherical or ovid cells, whilst others were decidedly ellipsoidal, and others elongated and sausage-shaped. No great advance, however, could be made in differentiating between the various species until the late Professor E.C. Hansen in 1879 showed how it was possible to obtain almost any quantity of yeast by starting with a single cell. For this purpose a very dilute mixture of yeast and sterilized water is first made, and a little of this is inoculated into a quantity of melted wort gelatin, that is to say, a moderately strong malt wort containing sufficient gelatin to cause it to solidify when cold. A drop of this solution is then examined by means of the microscope to ascertain whether it is sufficiently dilute in respect of yeast cells, that is to say, whether the cells are well separated one from another and are so far apart that the colonies resulting from their development could not possibly meet. If such is the case, a drop of the gelatin mixture is spread out in a thin layer on a microscope cover glass, on which it solidifies. It is then placed, with gelatin downward, over a small glass cell containing a drop of water to keep the gelatin surface moist. Several yeast cells, which are well separated from one another, are then picked out by microscopical examination and their position on the glass cover marked. The slide is then kept at a suitable temperature, and in a few days the development will have proceeded so far that the resulting colonies will be visible to the naked eye. When this is the case, a very small piece of sterile platinum wire is dipped into any one of the colonies, and then dropped into a suitable flask containing sterile wort. In the course of several days the wort will be found to be in a state of active fermentation, and a sufficient quantity of yeast will have been formed for the pitching of a still larger quantity of wort. Working in this way, and pitching each time into vessels of larger size, it will be seen that practically any quantity of yeast can be prepared, the whole of which has originated from a single cell. Pure cultures of the various Saccharomyces having thus been prepared, it was found that morphological characters were frequently useless for the purpose of distinguishing between one species and another, for not only did many of these resemble one another somewhat closely in appearance, but the shape of any one species varied within wide limits, depending chiefly upon the conditions under which it had been grown. This method of obtaining pure cultures when used in conjunction with certain other methods of differentiation, such as the behavior of the yeast toward certain selected carbohydrates and the optimum temperatures for ascospore and film fermentation, has enabled zymotechnologists to isolate and describe many distinct species, of some of which numerous varieties are known. It should be said at once, however, that only a few of these are of industrial importance. For technical purposes the yeast may be divided into two classes, the cultivated and the wild yeast. The former includes brewer's yeast in all its varieties, that is to say, the yeast which has from the very earliest times been used for the production of alcoholic beverages, and has, in a sense, been cultivated for the purpose. This yeast represents so far as is known one species, namely Saccharomyces cerevisiae, although many races and varieties are known which differ considerably in certain respects, as for instance in the rapidity with which they bring about the fermentive change, the degree of attenuation, i.e. fermentation, which they can effect, and the flavor of the beer produced. Of the Saccharomyces cerevisiae, There are two main types known respectively as top and bottom yeast. The former rises to the surface during fermentation, and is the yeast used in English breweries, whilst the latter sinks to the bottom of the fermenting tun and is used in the production of lager beer as brewed on the continent and elsewhere. The wild yeasts are yeasts which occur wild in nature, and frequently having their habitat on the surface of ripe fruits, often find their way into the brewery. Some of these wild yeasts, using the term in its widest sense, are capable of fulfilling useful functions in connection with cask fermentation, but others are highly undesirable. Although in his study of the various diseases to which beer is subject Pasteur chiefly concentrated his attention on the bacteria, he did not altogether overlook the possibility that certain of the yeasts might be pathogenetic in character. It will be obvious, however, that no definite information in this connection could be obtained until Hansen had shown how to discriminate between the various species. It was then found that certain species of yeast were as much to be feared as many of the bacteria. Thus, Saccharomyces pastorianus 1 produces a nauseous bitter flavor and a disagreeable smell. Saccharomyces pastorianus 3 and Saccharomyces ellipsoideus 2 persistent turbidity. Saccharomyces anomalus a pronounced fruity flavor. Saccharomyces elices a disagreeable bitter flavor, and Saccharomyces foetidus stench. The following photomicrographs will give some idea of the microscopical appearance of a few of these wild yeasts. Saccharomyces ellipsoideus, Fig. 8. Saccharomyces pastorianus, Fig. 9. Saccharomyces anomalus, film, Fig. 10. And Saccharomyces apiculatus, Fig. 11. The last mentioned organism ought not properly speaking to be included among the Saccharomycetes, since it has never been observed to form endogenous spores, but its appearance is very characteristic, and it often finds its way into the cooling wort. The following may perhaps be regarded as the more usual ways in which infection with wild yeast takes place. 1. Direct aerial infection, usually at the refrigerating stage, more rarely on the cooler or in the fermenting tun. 2. Indirect aerial infection, that is to say, by dust which has accumulated on prominent internal surfaces of the cooler, refrigerator, or fermenting tun rooms, and which has become dislodged by wind. 3. Surface infection, or infection due to nests, formed in the soft or old parts of fermenting tuns or yeast bacs. 4. Infection due to unusually impure pitching yeast, that is, the yeast used to start the fermentation. Owing to the tendency of culture yeast to oust the wild species, especially under the conditions of English brewing, it will not often be found that serious trouble can be traced to this cause. 5. Infection due to dry hopping, that is, the introduction of wild yeast with the hops added to the beer in cask. How the more important sources of such infection may be guarded against has already been pointed out in the previous chapter. Since even different races or varieties of the cultivated yeast, Saccharomyces cerevisiae, exhibit different properties, the introduction of the method of preparing pure cultures from a single cell naturally raised the question whether certain selective varieties, or even species, might not be successfully used in practice. Such pure cultures were first introduced by Hansen himself into certain Danish breweries with excellent results, and the method spread so rapidly on the continent as almost to constitute a revolution in continental brewing practice. For each brewery, experiments had first to be made in order to find out which of a number of varieties was the one best suited to the conditions obtaining in that brewery, and to the type of beer required, and then that yeast was cultivated in the necessary quantity. There can be no doubt that, as a general rule, the results have been very satisfactory, beers of greater stability, of more uniform character, and of better flavor resulting. A good many attempts to introduce the use of selected single-cell yeasts into English breweries have, however, met with much less success. One reason for this is that the conditions obtaining in most English breweries are such as to result in the production of a definite type of yeast, which gives the exact class of beer required, and which can without any special steps be kept practically pure, that is, free from bacteria and other yeasts within the limits necessary for successful working. In the second place, there is a greater difference in character between the main fermentation and the secondary or cask fermentation in English high fermentation beers than is the case in lager beers such as are brewed on the Continent, and it has not hitherto been found possible to obtain with a single cell yeast the proper cask fermentation which is so important a feature in English brewing. Having now considered yeast from the purely biological standpoint, it may be convenient to refer briefly to the question of its nutrition, that is to say, to the various substances which it requires for its healthy development, and then to consider how far these are naturally supplied in the brewer's wort. It has been pointed out above that yeast, like all organisms which are devoid of chlorophyll, cannot obtain its carbon from carbon dioxide, and it is, therefore, necessary to supply it in some soluble and assimilable form. The various carbohydrates represent one such form, and it is from these that carbon is to some extent, but not by any means entirely, obtained, and the necessary vital energy indirectly derived. Of the protoplasm, nitrogen is the most significant and important constituent, and dried yeast contains about 8% or more of that element, which is equivalent to 50% or more of protein matters. For the manufacture of its protoplasm, therefore, it is essential that sufficient nitrogen should be supplied to the yeast organism, and in the form in which it can be most readily absorbed and assimilated. Yeast is, in fact, able to satisfy its nitrogen requirements when presented with such simple forms as ammonium salts, but its development is more vigorous when the nitrogen is applied to it in the form of amino compounds, amides and peptones, that is to say, when it is grown in solutions containing the products of the hydrolysis of proteins. The more complex proteins cannot apparently be utilized, since they are not diffusible and cannot therefore penetrate the cell wall. Another element necessary to the life activity and well-being of the yeast organism is phosphorus, which is present in the form of nucleoproteins and to some extent as phosphate. Of the inorganic elements, potassium, magnesium, and to a less extent calcium are indispensable, as may be gathered from the following analysis of the ash of yeast. Average composition of the ash of yeast, Lintner. Potash, K2O, with a little soda, 33.49. Magnesia, MgO, 6.12. Lime, CaO, 5.47. Oxide of iron, 0.50. Phosphoric acid, P2O5, 50.60. Sulfuric acid, SO3, 0.56. Silica, 1.34. Matters undetermined, 1.92. Total, 100%. The need for oxygen has already been referred to. Now it so happens that all these necessary nutritive substances are normally present in malt wort, which constitutes in fact an almost ideal liquid for the nourishment of yeast. There are the carbohydrates, sugars, the amides, e.g., asparagine, peptones and other diffusible and assimilable nitrogenous substances, phosphorus as phosphate, and sufficient quantities of the salts of potassium, magnesium, and calcium. It does, however, happen occasionally, owing to the employment of malts of abnormal character, or to the use of larger proportions than usual of grain or sugar adjuncts, that the worts are deficient in the precise kinds of nutrigenous and other nutriment needed by the yeast for its proper development. In such cases the appearance of the yeast in the fermenting tun is such as to indicate that it is not receiving the food it requires, and the brewer usually endeavors to make good the deficiency by adding to the fermenting wort a quantity of so-called yeast food, containing the needful nutrient materials, and specially prepared for the purpose. Pressed yeast, that is yeast practically free from extraneous water, contains as a rule about 75% of water, present of course in the liquid protoplasm of the cells. The following analysis shows the average composition of dry yeast, and will suffice to give some idea of the proportions in which its more important proximate constituents are present. Average composition of dry yeast. Proteins and other nitrogenous substances, 51.8. Yeast gum and other carbohydrate matter, 29.5. Fat, 1.0. Mineral matter, 11.0. Matters undetermined, including some cellulose, 6.7. Total, 100%. End of chapter 6, part 1. Part 2 of Brewing by A. Chaston Chapman. This LibriVox recording is in the public domain. Read by Marianne. Chapter 6, part 2. Having now considered the nature of the yeast as a living organism, and having dealt with its food requirements, we may pass to a consideration of the interesting and important phenomenon which it is its special function to excite, and which is known as fermentation. Few chapters in science are more fascinating than that dealing with the elucidation of the mechanism of the process of alcoholic fermentation, a process which was deliberately carried out thousands of years ago, and which would scarcely fail to attract the attention of the first man who left a bowl of honey exposed for sufficient time to the air. To deal at length with this question would be impossible within the limits assigned to this book, and as many of the earlier theories are now only of historical interest, I propose to go no further back than the later views of Liebig. From the chemical point of view, fermentation consists essentially in the decomposition by means of yeast of a carbohydrate such as dextroglucose into alcohol and carbon dioxide, according to the equation C6H12O6 D-glucose equals 2C2H6O alcohol plus 2 CO2 carbon dioxide. As a matter of fact, the chemical reactions involved are by no means so simple as the above equation would indicate, since whilst 95% of the change takes place in accordance with that equation, about 5% of the sugar is broken up into glycerin, succinic acid, and other products. A small proportion of the sugar is also utilized by the yeast for the formation of new cells. In 1839, Liebig put forward the view that a ferment, e.g. yeast, is a nitrogenous substance in a state of molecular instability, and that it was a peculiarity of such substances that they were able by mere contact to communicate this state to certain compounds such as the sugars, causing these to break down into simpler substances such as alcohol and carbon dioxide. This theory of contact decomposition as the result of molecular vibration held the field for more than 30 years, but during the latter part of its life it was vigorously attacked by Pasteur, who was then engaged upon his epoch-making biochemical researches. The controversy was a long and vigorous one, and in the end Liebig so far modified his original views as to admit that the fermentation process was in some way connected with the life activity of the organism producing it. But he adhered so far to his earlier view as to hold that this life activity was not in itself the exciting cause, but was only necessary for the formation of some protein-like substance which actually brought about the decomposition. This theory, which was put forward shortly before his death in 1873, is of special interest in connection with the view which is now universally held as the result of comparatively recent observations. To Pasteur belongs the credit of having been the first to prove definitely that fermentation was a physiological phenomenon, that is to say that it was intimately connected with the development and general vital activity of the yeast cell. He found that when a small quantity of yeast was introduced into a fermentable liquid saturated with air (oxygen), the oxygen was quickly absorbed and the yeast multiplied freely. He further found that when the whole of the free